This is problem 37 from Chapter 16 of the textbook Stats Modeling the World, 2nd edition. So here, what we're looking at is what's called a medley. So it's kind of like a swim race where there's 4 swimmers and they swim 100 yards, and then one person swims 100 yards, and the next person swims, and the next person, until all 4 have gone, and each one does a different stroke or different kind of swim style. Okay, and so we've been given the average times of each swimmer for this race, and we've been given the standard deviations, and it looks like in seconds. So here's some of the assumptions. The swimmers' performance are independent, okay, and each swimmer's times follow a normal model, so that may be new. So we'll see how that plays out pretty soon. And then here are the times. Okay, so let's just get started. What are the mean and standard deviation for the relay team's total time? So the total time. So we could say let t be the random variable total time, such that t equals swimmer 1's time plus swimmer 2's time plus swimmer's 3 time plus swimmer's 4 time, like that. That might save some notation. So the expected value of t is just the expected value of S1 plus the expected value of S2 plus the expected value of S3 plus the expected value of S4, swimmer 4. So we get 50.72 plus 55.51 plus 49.43 plus 44.91. Okay, so I get 257 seconds. Okay, so now they want to know what's the standard deviation. Well, hopefully I have enough room. So let's start with the variance. The variance of t is just going to be the variance of S1 plus the variance of S2 plus the variance of S3 plus the variance of S4. But in this case, since the standard deviation is all different, then the variance is all different. So don't write this. We cannot write just 4 times the variance of S. It's not one of those. So don't do that. We are actually going to have to plug in each value. So that's going to be, the variance is going to be the standard deviation squared. So that's going to be 0.24 squared plus 0.22 squared plus 0.25 squared plus 0.21 squared. And let's see, I haven't actually done this yet. Let's see if I can use my calculator. So 0.24 squared plus 0.22 squared plus 0.25 squared plus 0.21 squared equals 0.2126. So 0.2126. So the standard deviation of the total time is just the square root of that, 0.2126. And let's just go back to the calculator. It's right there. Boom. We get 0.461. So 0.461. Okay, so that answers the question, what is the expected value and what's the standard deviation? Let's look at part B. Okay, now the team's best time for this season is 199.48 seconds. So the best time equals 9.48. Okay, do you think the team is likely to swim faster than this at the conference championship? Okay, so in order to answer this question, I'm going to back up to this assumption here. Since each swimmer's time follows a normal model, okay, so in other words, there's a normal model for the expected time of swimmer 1 and a normal model, so to speak, for 2, S1, S2, and so on. Then when you combine them, as we have done here, then T will also, the total time will also have a normal model. Okay, so let's think about what that normal model would be. Well, the center is the expected value, that's the mean, and we calculated that. It's going to be 200.57 seconds. So 200.57. Okay, we'll use this notation too. 200.57. This is good notation. It speaks to the AP test reader. Okay, now the standard deviation, so you want to tell the reader that you know the standard deviation of this model. It's 461. So you're really saying a lot when you write this notation. Okay, so now the best time, we want to know, do you think the team is likely to swim faster than their best time? So their best time is over here somewhere. I'm not quite sure where, but it's certainly going to be to the left of the mean. It's somewhere over here. Okay, so do you think, well, so I think what they're asking us is, what's the probability that their time will be, faster would be less than the best time, 199.48. Okay, so what that's saying is, what is the area? That probability corresponds, is proportional to the area under the curve right here. Okay, so we could say that's going to be, and we have to do our z calculation now, because we want to find the z value on the standard normal model. We want to know z. So z, that's going to be less than, and I'll just make a little note over here. Remember that z is equal to the observed value minus the expected value divided by the standard deviation. So the observed value that we're interested in is 199.48, and we're going to subtract off the model's center, the mean, 0.57, and we're going to divide by the standard deviation. There it is, 0.461. Okay, now that's going to be the probability that z is less than negative 2.36. Okay, and so we can get that by using your calculator. Remember that if you can find this function, normal CDF, we can find that if you do second distribute and then go to, I think it's 2, normal CDF. Okay, and so since we've already converted to z, then we just want to go from negative infinity to our z value of negative 2.36. So we'll approximate negative infinity with a bunch of 9s, and then we'll use negative 2.36. We always go left to right. Okay, and so that comes out to be 0.009. And if you want to think in percents, that's 0.9%, so less than 1%. Okay, so the team is not likely to swim faster than their best time. According to the normal model, they are only expected to swim, let's see, that fast or faster 0.9% of the time. So that's not very often. Okay, so that's how you do this problem. So we're starting to incorporate using the normal model, but you can only do that if they tell you that it follows, that the random variables follow a normal model. Otherwise, we can't do it.